Okay, so we take off from where we left in the last class. We had found out the strains, the normal strain epsilon x, which was along the neutral axis for a pure bending situation. And then we had also made an argument that why the shear components, make this correction, would be 0. So this is something which was left out to you uh, for doing, how you would individually prove that these two shear strains are 0. We did not make a comment about epsilon y and gamma yz and epsilon z in the last class. The reason was that we didn't know anything about it, and we still don't. So what we leave over here is that they must be symmetrical with respect to the xy plane, which was the plane of symmetry. So your epsilon z has to be symmetrical about the plane of symmetry. Same would be for epsilon y, and automatically gamma yz as well. Okay, so we did not make this comment in your textbook. You should just check whether you have epsilon y, epsilon z and gamma yz. Okay, so I think this is wrongly written in your textbook, which you can make a correction. So the next step, I mean, remember 2.1 has three parts. One was about the force equilibrium, the second was about the deformation, geometric compatibility, and the last is about the relationship between force and deformation or stress and strain. So right now we have done the second part of it, which was about the deformation strains. Yet we will now be going to the third part, which is the relationship between stress and strain, and finally we will come back to the equilibrium requirements. Okay, so the same steps in a different order. So section 7.3 is about stresses obtained from stress strain relations. Okay, so stress strain relations. So we have enough number of strains as of now. Let's see what we can do with it. So the arguments which have led to 7.4, this is 7.4 and this is 7.5, are independent of the beam material. I mean, as I had always said, I mean, the theory of strain is independent of the theory of stress. It is the actual stress and actual strain at a point which can be related if you know what kind of a material that is. Okay, so if the material properties do not change along the length of the beam, then these properties are also symmetrical with respect to the xy plane, and hence within these limitations the material can be non-isotropic, linear or non-linear, elastic or plastic. Okay, so in reality you can have any sort of a material, but we will restrict our discussions to always as linear, elastic, isotropic material. Okay, because we are just beginning into this solid mechanics right now. Okay, so we'll do that and we'll utilize the Hooke's law, and for that we will be able to use the Hooke's law. So let's recall what the Hooke's law was. It was epsilon x equal to 1 by e. We had made all these derivations. Okay, at this time you should, as soon as you see these equations, you should be able to recall those derivations and the reasonings behind them. Okay, so this will be equal to minus y by rho. Okay, it's coming from over here, and gamma xy would be equal to tau xy by g. This is equal to 0 because of this equation, and similarly gamma xz will be equal to tau xz by g equal to 0. Okay, so we learn that the shear strain tau xy and tau xz is also equal to 0 in pure bending. Everything is there for pure bending only, when MB is not changing along the length. So the shear stresses are 0. This is something which we learn right away from these discussions, and of course we are inconclusive about many other things, but let's focus on what we know for now. Okay, the other gaps will fill later on. Okay, so the next part is about the equilibrium requirements, and remember we had argued that at one point, that I think in the start of this chapter, that our aim in this chapter, this is section 7.1, our aim in this chapter is to determine the distribution of stresses which have the shear force V and bending moment MB as their resultant. So the stresses which we are finding, they must be such that their resultant is the shear force V and the bending moment MB, and that relation we will achieve through the following equilibrium equation. And this is the third step. In 2.1 it's the first step, but it's the last remaining step. So let's see. So you want the resultant of the stress distribution over the cross sections of the beam should be equal to the bending moment as indicated in 7.6. So let's see. You have a, let me just zoom in slightly. Okay, this should do. Okay. So we have the beam, the coordinate system is shown, and just like always we have a neutral surface. So the surface which contains the neutral axis is the neutral surface, and it is perpendicular to the plane of symmetry. Okay, so that is what we had seen, and the x-axis is aligned with the neutral axis itself. So let's take a small element sigma x delta A over here. Okay, we have cut a cross section, and where is this element located? It is located at a distance z from the y-axis and y from the x-axis, and it is located at x equal to 0, needless to say. Okay, so this is where this small area is located, sigma xa, and this is the force which we would consider because we multiplied by delta area. So as soon as you have a force, remember the equilibrium equations only are in terms of the forces and the moments. So once we have that, we will balance the forces in the x direction. What would that be? That would be an integration over sigma x dA equal to 0. Clearly delta A is tending to 0. And then you would have the bending about the y-axis. Okay, so you would have sigma x into dA, which is the force, and the lever arm in this case would be z. Okay, and this you would integrate over the area, and this value is 0, which is given to us because the only bending moment which we have is along the z-axis, right? So mz will be equal to a sigma x dA into the lever arm about the uh, lever arm to calculate mz is y, and this is equal to mb. Okay, so these are the three equilibrium equations, and that's what essentially is the fundamental of this part. Now here we again make the fundamental assumption that the deformation of the cross section is sufficiently small so that we can use the undeformed coordinates to locate the points on the deformed cross section. Okay, so when we chose this element y, we chose this element z, it was in the undeformed situation, but we continue using the y and z even in the deformed configuration, because that point of concern, the center of this area, has deformed only slightly. So this is an approximation which we make, and we have made in the last case as well. I mean, when we assume this y to be the same as this y, which was in the undeformed case. Okay. Okay, so, and this what you are, the assumption which you are taking is not very uncommon, in the sense even when we study advanced courses in linear elasticity, we always want to use the undeformed configuration as our reference. so that it is easy for us to find. For example, and the same will happening over here. You should see what I am explaining now can actually be applied to over here. Say you have this 2D plane, okay, undeformed, and consider this point over here, okay. Now you pull this point, and then clearly this will deform in a certain way, and most likely this point say may have moved up to this point, okay. So this point has moved over here, and hence this will have a stress at this particular point, okay. So despite knowing that the stress and strain only act when there has been some deformation, we still say that the stress at this point is what we have found out. Stress and strain at this original undeformed point. Even though the point has now moved here, we say that the stress and strain which we are finding using the theory of elasticity as this undeformed point. And you may have learned in your fluid mechanics about Euler and Lagrangian ways of looking at a problem. So you will notice the difference between solid and fluid mechanics. One of them uses a Eulerian method, the other uses a Lagrangian. So which one is that is something which you should think about and perhaps talk about as well. Okay. So that is what we have done in section 7.3. So let's 7.4, I'm sorry. So let's now sort of move ahead and see this section 7.5, okay, which is the stresses and deformation in symmetrical elastic beams subjected to pure bending. So the purpose now is to, be able to find everything which was remaining. Until now we have found some stress components, some strain components, and then we relate it through the equilibrium situations. Now we would want to put the missing pieces into place. Let's see how that can be done. So our aim is to draw out the solution which meets the requirements of 7.6 and 7.7. So 7.6 was this, sorry, 7.6, and this was 7.7, which is the Hooke's law stress and the equilibrium. So we want to now find out these values. Right now, for example, we don't have sigma x is equal to something, right? Sigma x is somewhere implicit in this, and then sigma x is implicit in this. So we don't have it in the open form, explicit form. We want to do that first. Let's see how we can do that. So, and we obviously sigma x and sigma y and other whatever else we have must satisfy those equations 7.6 and 7.7. Okay. You can always say that we can write using this equation sigma x is equal to something, but you see you will have this sigma y and sigma z sitting over here, and we don't really know much about them. Okay, so it won't take us very far. So there has to be some other method, and it seems there is no way ahead to move, and hence the assumption which we must take is about the transverse behavior. So remember in chapter 1, in one of the problems we reached a stage and then we said we are up against the wall, okay, and hence we had to make some simplifying assumption. So a similar stage has come over here. We have exhausted everything which we knew, and now there is no other option but to take these assumptions about the transverse behavior in the sense which involves Z. So let's see how that works. In searching for a reasonable assumption, okay, this is the language which we use. We know that we have to take assumption, so let's look for the most reasonable assumption and not something which may be absurd to start with. So we observe that the external forces of the elemental slice of thickness delta x in 7.8 are free of normal and shear stresses. So if you take a element of slice, elemental slice of thickness delta x, this is that slice of delta x, okay, which you see over here. We observe that they are free of normal and shear stresses. Can you see that they are free of normal and shear stresses? Look at this external surface. This external surface is free of normal and shear stresses. Okay, we know that. I mean, this is the beam which we are bending, and hence we know that the surface which is outside, it does not have any stress. Actually, the boundary conditions are always about tractions, which is about the stress vector, but in this case the stress vector and the stress components will be both zero. So you want to check the boundary condition, you can always write that the stress vector is zero, then multiply the stress components with the normal vectors and then equate them equal to zero, and you will come to the same conclusion that it does not have any normal or shear stresses. So this is what we say, that the external surface of this element are free of normal and shear stresses. Now the slenderness of the beam, remember this is one word which we used earlier on in this chapter, our slender beam, suggests that the plausibility of assuming that the transverse stresses sigma y, sorry, let's do that over here, sigma y is equal to sigma z is equal to tau yz is equal to 0 throughout the interior of the beam. Okay, so sigma y, sigma z and tau yz. So this is the idea. Let me draw this delta x. When you try to look at it from the front, let me draw the whole delta x. I'm just drawing this. Okay, I'm showing this rectangular. So this is delta x. Okay, just taken the coordinate system because of the stresses are in the Cartesian system. So it is clear that this does not have a normal stress, which is sigma y. Okay, this shaded element, and it does not have a sigma y. It also does not have a sigma z. Okay, and it does not have tau yz, meaning on the y plane in the z direction. So I am trying to look at it from this side. This is my eye and I am trying to look from over here. So this one, okay, tau yz. So these things are all zero on the surface. Everyone understands that because it is easy to see that there is no such thing on the surface. Now, what is the argument which makes us say that these values are zero within the surface also, within the solid also? And the argument is this, and I think we have discussed it at some point, because it's a slender member. Remember what a slender member was? The length of this is much greater than any other dimension. Okay, so it is greater than, say, this dimension by a lot. So this dimension is negligibly small compared to the length. So this dimension is actually this dimension. And the logic is this, that sigma z is equal to 0 over here, sigma z is 0 over here, and this, because this is too small, this length, so it is very unlikely that it will take up a reasonable value and then come back to 0. So most likely it will not have, because it does not have that enough distance to go up and come down to a reasonable value. So it can be assumed that it is almost 0 within the thickness as well, and that is what we have taken for sigma z. The same would happen for this dimension, which is small compared to the length of the beam. So take this dimension, and again sigma y is 0 exactly over here at the surface, it is 0 exactly here at the surface, and because this distance is so small, it is unlikely that it would go up and come down to 0, hence it is reasonable to assume that it will be about 0. If the distance was big, then yes, you could have this. Okay, if the distance was finite enough, then you can finitely large enough, then you can have this possibility that it will go up and then come down to 0. But since it's not, it can be taken as 0, and the same would apply for shear stress tau yz as well, because they are also 0 at these surfaces. This is also the same argument through which in plane stress you take sigma z is equal to 0, because the out of plane direction the stress is 0 on the surface, and since the thickness of the specimen is so small, it is assumed that sigma z is throughout 0 in the bulk as well. So that is the argument through which we are able to write like this, and this is the assumption which we are talking about. Okay, so let's now see with this assumption. So this assumption is 7.8. We are left with only one non-zero stress component. Okay, let's see which are the ones which we have found out. Let me use my other color, which is green. Let's use this green. Okay, so we know about 1, 2, 3, we know about 4, we know about 5. Only thing which is remaining is which element? I mean, there are only 6, right? Because of the symmetry, there are only 6 stress components at a point. That unknown is sigma x. Only this is unknown. So how would we find this? You can go to 7.6, okay, and then put sigma y is 0, sigma z is 0, and then sigma x is left out. Okay, so sigma x would be equal to, I should come back to my pen, sigma x would be equal to minus of E y by rho. Okay, and this would be minus E. Remember what rho was? 1 by rho was, it was d phi by ds into y. So this is what the normal stress is, and hence we have found out all the remaining stress components. Okay, so that's a good achievement. Obviously it took us an assumption, and believe me, this assumption works. Even it, I mean, there are many experiments which you can do to confirm that this is a reasonable assumption to take in case of a slender member. Okay, in case of the slender member in which one of the dimensions is too small. Okay, now we don't make this mistake along the thickness length. I mean, if there was a situation in which the force over here was 0, the shear force over here was 0, please don't assume that there would be no shear stress in the interior for this bending. No, I mean, that won't be happening. Okay, just because the same logic will not apply then, because it gives a lot of time for it to rise up from 0, go to some other value, and then come back to 0. Okay, so this is the longitudinal normal stress distributed in pure bending of a beam whose material follows Hooke's law. This linear variation of stress with distance from the neutral surface. Y is the distance from the neutral surface, if you remember. So this linear variation of stress with distance from the neutral surface was used for stress distribution illustrated in 7.6a. So 7.6a, look at this stress distribution. It is increasing as you go up, fine, with a negative sign. So you see the arrows, sigma x is pointing in the negative side despite y being positive. And similarly, if your y becomes negative, then this becomes positive, and it is shown by these arrows. So the same stress distribution is shown, and you are easily able to now visualize why this stress sigma x will vary like this on this plane. Okay, on this plane, how will sigma x vary? It will vary like this. At the neutral surface, it would be 0 because y would be 0 at the neutral surface, and hence sigma x would be 0 at the neutral surface. So neutral surface seems to be having quite a ball, right? Anyways, all the other stress components were 0. The only non-zero stress component sigma x would also be 0 at the neutral surface. Okay, so now the last part which we would want to study in this section is how to locate the neutral axis or neutral surface as such. Okay. So we now continuing now to draw out the solution. We substitute 7.9, this is 7.9, into first of 7.7. So you want to put this into this, which is the first of 7.7. So once you do that, you will put sigma x over here and then integrate it, and you should find out that sigma fx is equal to a sigma x dA is equal to minus of a e y by rho dA equal to minus e by rho a y dA is equal to 0. Okay, e and rho can be brought out, and this is what we get. Now this result tells us that when linearly elastic beam of constant modulus E bends, that is when E by rho do not vanish. So this is not something which vanishes. That is what will ensure its bending, right? I mean, there is a curvature. So since there is a curvature, we know that it is bending. So this first component of the cross-sectional area about the neutral surface must be 0. So what this implies, if this thing is not 0, then this implies that a y dA is equal to 0. So this is the first moment of the cross-section area about the neutral surface axis. So this is the area and this is y. So y dA is equal to 0. Stated otherwise, the neutral surface must pass through the centroid of the cross-sectional area. And this is how I know that neutral surface must pass okay. So this is the conclusion which we can make, that the first moment of the cross-sectional area above the neutral surface must be 0, and that means that the stated the neutral surface must pass through the centroid of the cross-sectional area. Now, can you think of why from here to here you can come? I mean, what is making you think about this? Okay, why do you think that when this is true, this can be said? I mean, I'm speaking about an unrelated theorem, but you can think from that perspective. But the good thing is there are many other ways to conclude this. There is something called a zero value theorem. Okay, what it says is that if you have an integrand f in which you are integrating over the entire volume V, and this is 0, and because this small volume V dV over which you have found this value is arbitrary, you will have f is equal to 0. The integrand itself must be 0. Okay, so this is something called the zero value theorem. See if you can apply something like this over here. Okay, or any other method is fine as well. Okay, don't constrain yourself to any one method, but see if this helps you. You must have heard about this theorem or known this theorem in some other way. Okay, so moving ahead, it should also be noted that for linear elastic beams made of more than one material or beams whose material behaves in a non-linear fashion, the neutral surface can still be located by sigma fz. So the equilibrium will always be valid even when you have a non-linear material, meaning, see, this equilibrium condition does not care about what your kind of material is. It can be linear, non-linear, elastic, plastic, does not matter. These equations will always be valid. It is here when you use the Hooke's law, you constrain it to a linear isotropic material. Okay, so that is the comment which they are making over here. Okay, now substitute this 7.9 into this and then into this. Okay, substitute this 7.9 into this 7.7, 1 and 2. So once you do that, you will have a sigma my is equal to minus E by rho a y z dA is equal to 0, and sigma mz is equal to E by rho a y square dA is equal to dA is equal to mb. Now this, let's see this integral. I mean, the same argument applies if the bending is happening, in the sense curvature is not 0, E by rho is not 0, then the only possibility is that this is 0, and this means that because of the symmetry of the cross section with respect to axial plane, thus the second of 7.7 is satisfied. Okay, the integral on the right in 7.11 is 0 because the symmetry of cross section with respect to xy plane, and thus the second of 7.7 is also satisfied. So this particular thing is 0 because let me look at that plane. See, yeah, this is the area. You have a delta A and yz into delta A. So if you have y, you have z, and on this yz, so meaning if you are over here, now you take another point, another area which is over here, y, and at minus z, okay, it would cancel out because this symmetry plane is arranged like this. And similarly, if you take for the same z area over here which is at minus y, it would cancel out from this, and that is how this entire term can be yz dA will be equal to 0 because of this symmetry. Okay, so you are able to satisfy this, and okay. Now the same has to be done over here uh, for sigma mz, and you find that this would be equal to mb if you look at this particular thing. So for this you were actually checking when this is 0, okay, but since you have verified that this one has to be equal to 0, so is the case over there. Okay, now let's take one more sort of thing. Okay. I mean, this statement, I think by this time you can figure out that this was not really needed, and this YDA, I mean, if you take this area over here and then you take minus y, you will get a negative, you will get a value which is opposite, and it will cancel them out. So for every y, there will be a corresponding minus y, and that tells us that your neutral surface must be somewhere over here, okay, passing through the centroid of this. Okay. So coming back to this equation, the integral on the right in 7.12, this one is known as the second. So this is called the second moment, okay, of beam cross sectional area, just like this was the first moment of beam cross sectional area. And this is also called the moment of inertia of the area about the neutral axis. So it can be computed once the specific shape of the cross section is known, and we'll just call it as IZZ. So if it's a rectangular one, you would know what it is. If it's a circular one, you would know what it is. So in APL 100 itself, I think you have done enough of these things to do this. Okay, so we'll just write. So this is the IZZ is called the moment of inertia about point Z, and then there are some properties of it which you perhaps have learned before. They are also there in problem 7.5 and 7.9 if you need to recall them. Okay, so let's see what it means now. You want to now substitute this MB. So let's see, df d phi by ds is equal to, so this is just like writing rho is equal to 1 by rho is equal to mb by e izz. When the bending moment is positive, the curvature is positive, that is concave upward. So if the bending moment is like this, the curvature will be like this. This you can do by merely bending a rubber eraser. Okay, so that is what it means. If this is positive, which means it's a concave up like this. Okay, now you want to substitute this equation in the earlier expressions of strain. So epsilon x is equal to minus mby by eizz. Okay, so I think this expression in 7.4, so I think over here, this one. Okay, so d phi by ds you already have found out in terms of the bending moment and izz, so you just substitute it over here and you will get epsilon x is equal to this, and sigma x is equal to minus mb by y by izz. Okay, so this is the we express which expresses the longitudinal strain and stress in terms of the applied bending moment, and so we have found out this value in terms of the bending moment. Remember, bending moment is just like your mt, which was the twisting moment, or F, which was the axial loading which you were applying. Okay, so it's an external applied force, and this you find out what the stresses and strain they will develop inside your beam when it's a pure bending situation. Okay, again we note that the stress distribution is linear. You can see that it's linear in Y, and from 7.16 that the fibers on the top of the surface are in compression while the fibers in the bottom surface are in tension. So we have already seen that. This just verifies those observations. Now, just to complete and find the other stresses, other strains, so we found all the stresses, we found epsilon x. There are some other strains as well which were left out. So remember, we were inconclusive about epsilon y, epsilon z, and gamma yz. So let's see now whether we can do that. So we want to now substitute 7.8 into 7.16 and now use the Hooke's law. Okay. Now please go to Hooke's law, which is equation 5.2 in your textbook. Okay. Please go to equation 5.2 in the textbook, and there you would find that epsilon y can be written as minus nu epsilon x, and epsilon z can be written as minus nu epsilon x. And you know what epsilon x is, so you can just put it, and gamma xz will be equal to 0. So the transverse strain components are this, the longitudinal ones you had already found out. So that perhaps solves everything, all the stress and all the strain components involved in pure bending, and that happens at any plane, at any point in a cross section. So depending where you are with respect to the neutral axis, the value will clearly change. The only condition is that MB has to be constant, because that is one of the postulates of a pure bending. Okay, so thus there is deformation in of the cross section. Well, we now see it quantitatively. How much is the deformation in the cross section? The normal strains in the plane of the cross section are proportional to the axial normal strain, but of opposite sense. There's a minus sign you see over here. Since the axial normal strain is compressive at the top of the beam and tensile at the bottom, the top of the cross section expands while the bottom of the cross section contracts. So that part you can see using this epsilon y and epsilon z now. So you can see where z is, epsilon y and epsilon z is. Okay. Since the axial normal strain is compressive at the top and tensile at the bottom, the top of the cross section expands. So along EZ will expand. So EX will contract clearly, but EZ will, epsilon Z and epsilon Y, they will expand. Okay, the deformed shape of an originally rectangular beam is shown in figure 7.9. So let's look at this figure. Let me zoom it in a little bit. Okay. The deformed shape of an originally rectangular beam is shown in figure 7.9. So we take a rectangular beam now, because this will already be a complicated geometry. So just to make it slightly simple, we'll do this. Okay, and there is our result of epsilon z implies that lines in the cross sectional originally parallel to the z axis have deformed into arcs of circle. So let's see epsilon z, that was equal to, sorry, it was nu into mby by izz e Our result of epsilon z implies that lines in the cross section originally parallel to the z axis, okay, have deformed into arcs of circles, okay, and in particular that the trace of the neutral surface on the cross section has become an arc of curvature minus nu by 1 by rho. So let's see where you can see that. Okay, so this is the whole idea, that I mean, if this has become an arc like this of rho, okay, of curvature rho, something like this would have become for epsilon z, okay, because it is in the negative sense, so it will be concave down, and the ratio would be minus nu by rho in this case, okay. So just like there's a minus nu factor over this. Now this transverse curvature of the beam is called anticlastic curvature. It can be seen quite easily if a rubber eraser is bent between the thumb and the forefinger in the manner indicated in this figure. Okay, this is how you must be bending the rubber, and you should be able to see how the deformations in this Z. So right now, I mean, as I've said, I mean, I used to tell you that please draw certain lines. So you were drawing maybe a line like this and a line like this. I would also request you to draw a line like this and a line like this, and see what happens to these lines when you try to deform. Okay, if you are able to get a lengthier rubber, that's even better. Okay, as a result of anticlasting curvature, the deformed neutral surface is a surface of double curvature. So look at figure 7.9. You will have a double curvature on this, the neutral surface. The deformed neutral surface is a surface of double curvature. So it will be curved along two ways. One is this curvature, and the other is this curvature. So this is what is mean, and this neutral surface looks like this. Okay, definitely not plane. Okay, this is what is happening over there. Okay, a further result of the anticlastic curvature is that the neutral axis is the only line in the deformed neutral surface whose curvature is in a plane parallel to the original plane of symmetry. So for this neutral axis, I'll just remove this now. For this neutral axis, the curvature will lie in the plane which was parallel to the original. But any other line which you see, their curvature will not lie in the originally undeformed plane, okay, because of this double curvature surface. Only the neutral axis has that privilege. Okay, so we have sort of discussed them, most of these ideas now, and we would want to study and take up certain problems which will be coming up I think in our next class. Okay, so let's take them and see how we can apply all these theories into practice. Thank you.